We've all been there. We have discovered a problem. Something catastrophic has happened, and you have had the bad luck of discovering it. It could have been a mistake you did yourself, or it could have been something that a colleague did. But all you know is you have been the one to discover this bad news. And you know this is going to cause problems for people further down the line. This is going to annoy some managers, annoy people in other divisions. This is a problem. So you do this very, very slow walk down the corridor, going towards the manager of the project, the next person, the phone call to the customer, something that's going to go wrong. And we're going to give the example that you have discovered a failed EMC test. That's what we're going to talk about today to give it a bit of context. So you've discovered this failed EMC test, and you've had to go over to your manager, to the customer, to someone, and you've had to show you can't make your project now. You can't actually go further. But let's give this a bit of context. Let's go back a step, all right? Let's rewind a bit. How did we get to this moment? How did we actually end up walking down the corridor in order to speak to your manager? How does a project actually work? Well, first of all, you have that initial concept. You have that time where maybe it's on a whiteboard, or you could even be in a bar with a friend and you've written something down on a napkin, the initial development of the initial idea of the project. Then it gets signed off, and then we're going to go in development. Right, we're going to change this idea into something functional, and then we're actually going to make it a productionable device. After that, there'll be some type of testing. Does the device do what it's actually meant to do? And also, is it safe? Is it going to blow up? Is it going to be able to withstand different temperatures? If it's something that's going to go on the outside of an aeroplane, is it going to be able to survive in Siberia and be able to survive in the Sahara Desert? Or also, is it going to interfere with other devices around it as well? Then after that, you'll have production. And in certain companies even, there will be a certain slot within a factory. And you might even have, years down the line, the exact moment when you have to have your device made. Then after that, very importantly, you deliver the device to the customer, to the project leader, to the market, and normally there's a fixed date as well, and you've got all the marketing team and your customer is all ready to actually receive that product. But what's happened is, we failed an EMC test. And this could be towards the end of your testing. So then what has to happen? Well, there has to be some type of redevelopment now. You have to take engineers that possibly are working on something new, and they have to be re-put back onto it. You might have to redesign the circuit board, redesign the enclosure, and now this is added a delay. You have to do further testing. The marketing guys and the customer is going to be screaming because of this problem. It might not even be yours, but you're the one who discovered it, and so you're feeling bad for everyone. Production had to be pushed out, maybe you lost that slot, maybe you had to go and wait later on before a revised date. So we're going to talk today about trying to avoid this situation. So let's delve a bit deeper into an EMC test. What actually is it? This is a chamber where the EMC testing is done. If you imagine a large room, a bit like a sound recording studio. And you know, if you've ever been inside one of those, you can't actually hear your voice, and that's because there's no reflections that actually come back off the walls, and that's because the sound and the energy is actually absorbed by these foam shapes that are on the outside, and then because of that, there's no way of it reflecting back. And also the way that it's protected is to stop energy coming into it as well. And the reason that this is important is because this is where EMC tests are done, of a certain type of radiated emissions and of conducted emissions, to make sure it's a fair test, so that every single product that is made in the market, every single thing out there, doesn't have the ambient energy from everything. So if it was tested in here, there'd be Wi-Fi signals all over the place, there'd be 4G and 5G signals in your phones. It wouldn't be a fair test if it wasn't measured in somewhere like this. And then inside there, we have these antennas. So if you focus on a radiated emissions or radiated susceptibility, which is where you're checking what is the device giving off? Is there radiation coming off it? And can it survive radiation being put towards it in what is expected to be a normal atmosphere? And so the reason would be, let's give it some context. Say that it's a device that's in an aircraft, and you have a radar system, and that is bringing radiation, or It's bringing an RF signal inside the cockpit so it can be actually read. You don't want that affecting the controls. You don't actually want there to be problems with it. So you don't want that part of the module to be giving off too much radiation, and at the same time you want to make sure that a device is capable of surviving that certain amount of radiation at the same time. So what happens is the device is set up inside of this chamber. This is a guy called James that I know quite well, and also the antennas are pointed in different polarizations, which are according to the specs that we'll talk about now. And at the end of the testing, because what it does is this antenna, if we're talking about a radiated emissions test, it will listen through the frequencies, and it will go all the way up according to the specifications, listening out for what actually is coming out of the device, bit by bit. And if you ended up in some graph like this, below the level, fantastic. And in fact, this would be one of the tests where, you know, if you had been a test engineer, you go through, oh, I'm not even going to bother worrying about that. I just flip the page because it's done. You know, there's no problem about it. But how is this test actually made? So there are standards. It's lovely bedtime reading, by the way. If ever you've had to go through standards and find the exact information. Has anyone done this? Who's had to delve down and find exact test? Oh, it's lovely, isn't it? So we all enjoy it. But it's got to be done, because this is the detailed instructions of how to do this test. Again, making sure that it's fair. And the test in particular for the MIL standards, so there's also other standards like DO160G, which is an aviation standard, but one which is very useful because you can get them online for free normally, are the MIL standards. And so the one which refers to what we're going to talk about today is MIL standard 461 version G. And then if we were going to delve even further into it, it's actually chapter 5.18, which is actually the radiated emissions test. So yes, you will have had to go through a lot of other chapters to get there. And inside that, it gives very detailed amounts of information for how this test needs to be set up. So first of all, you'll have a table. You'll have a specific place at a specific height where the unit under test needs to be placed. You will have an antenna behind it if you're talking about a radiated test, and that is at a specific distance away at a specific height as well. After that, you'll have a coaxial cable that actually comes out the back of it, exactly behind the where the antenna is, to make sure that doesn't actually interfere. That will then come outside of the chamber, and it will be on a on the device which is actually listening, because that could be giving off its own radiation. We don't want that to interfere. And then we'll have the recording device, maybe just a computer, just keeping track of the results. And this is what hopefully we would end up with. But then also, when they're calibrating the test, they also listen to it with no device in it, so that's one. And also they'll use a signal generator as well to calibrate, is it actually on the levels that we expect? Is the rest of the test setup actually working the same? So there's a lot of information here, a lot of detail of how this test is actually run. But also, an interesting part of the specs is, and we'll talk about quite a lot of this later on about the application, is that pass-fail level, what is actually allowed, depends on the application. Where is the device actually used? And I'll go into this in a couple more bits of detail. Let's imagine a submarine. Who's watched Vigil recently? Who's watched it on the BBC? Anyone? Just you? Can't be, it was cracking. Right, so in this series about a submarine, so the job of a submarine is to be very, very quiet and just to listen, and for it to be completely in secret, not to give off its position. So you can imagine if there's a device on the outside of the hull giving off radiation, which you've designed, and you failed your EMC test on it, you can imagine that's going to be a bit of a problem and it's not going to be allowed to go onto it. But then inside the hull, where you can imagine there's probably radios, there's computers, there's laptops, because that's sealed inside it, you can imagine that there would be a more tolerant amount of radiation that it could survive. And hopefully that's a good example. And this is why this graph is actually from the specifications, and you can see the different levels that actually it is permitted depending on the application. And there's different for tanks, different for aeroplanes. So going back to the original problem we were talking about. So in a perfect world, this is what we would have ended up with, but you have discovered, you're the one, oh no, we've got a problem, you've discovered this test. It's raised up further up, the noise floor generally is higher, and then we've got some points that it's actually pushing across. So what can we do about this? What could we have done before and after? Tiny bit of background. The odd time I have to go into some depth on it, but for those of you who aren't aware, wavelength and frequency. When you have a repeating pattern, the wavelength is the distance from, so for example here on the sine wave, it's the distance from the two crests from the middle. Hopefully we all remember this from school, but it's important that you remember that for the sake of the next bits. And then if you keep the amplitude of the same of it, and then you make the frequency higher, the wavelength will get smaller as well. And then that actually affects what is the end application, what's it used for. So a Wi-Fi signal, the wavelength is about this. If ever you've seen a Wi-Fi antenna, a long, a lower radiation, a lower frequency waveform is actually used with much larger antennas, and that changes the application as well. Now, a real interesting point that I want to bring up. This is an old-fashioned cassette recorder. Some of you youngsters maybe never used them, but I did quite a lot. It was a big part of my youth, recording some program. And just an interesting point to focus on with EMC. The most important point, or one of the fundamental rules of thumb we can think about, is the slits. And what's the longest area that a wavelength could actually fit through? It's not the area. So here this is a single box, and for argument's sake, let's imagine all the electronics in it is exactly the same. So if we had a double cassette recorder here, and we had two slits, the results are actually quite similar. So you might think, well, I've got double the amount of slit, that's going to let in double the amount of radiation, but actually it doesn't occur like that. You actually end up getting very similar results, because it's all about what's the largest, the longest wavelength that can go in. And it's a good rule of thumb to think of when we're doing our designs. So if we think of a box, if I just had an open box and just a flat touching on it, let's give some screws just for some, argument's sake, you can imagine that there would potentially be some slits which could let out radiation or let radiation come into it. And that's where we can choose the choice of enclosure just to help this. And this is just a tiny thing that can help with sorting out our EMC problems. So what we actually have is, in a certain type of enclosure, you just have a lap joint. So instead of it being flat, you actually have a little lip on the inside, just a couple of millimeters, and this can make quite a large difference to EMC performance, even though it's just what we believe is a tiny thing, as you can see here. So, and another thing as well is, also you can put gaskets, that I'll talk about in a minute, around the inside of it as well, to make it a very snug, tight fit, to make sure that there's no gap, to make sure that the radiation can come through. Okay, that's great. So we realize things need to be completely covered, no slits inside a box. Brilliant, but that's not a lot of use for the world, is it? I mean, if I've got one box, it can't be completely sealed, because I need it to talk to something else normally. I need it to somehow get some communication across. This is the world we work in. And then inside it, for argument's sake, there can be some PCBs inside it, so I've got two separate things. This could be like I talked about on the aeroplane earlier on, where you've got the radar, you can have a cable coming from the actual antenna itself, and then you'll have the receiving part and actually where it's displayed. So how are we going to do this? Well, it's quite simple, isn't it? We'll have a very long bar, and we'll weld it from one side, and we'll weld it to the other side, and we'll have it exactly put, and we'll have a nice long place where we can feed the cables completely and utterly put together with no problems here. Yeah, all of you are laughing. That's not going to really work, is it? Okay? So forget about this idea. That's a bad suggestion. This is where the world invented connectors. And if ever you lot speak to me later on, you'll realize I'm a connector geek. I really need to get a life, but I find new models and new different types of ways of solving solutions, and I do get quite excited because I know normally people have more things they'd rather spend their time on than connectors, than hunting the internet trying to find the right solution. So then when I find a good solution up front, and then when there is talented engineers out there in the world, and I know that this can solve their problems up front, that's why I really love connectors, to tell you the truth. So we're going to go into it. Let's imagine then I've got my sealed box, and I've got the connector coming out of it, and I've got these cables coming out. Let's put it inside the EMC chamber, and let's blast some radiation towards it. Let's see what it's like. Can it survive? Well, obviously, if you've just got some wires coming out of it, this would be an exceptionally badly designed connector, because long pieces of cables, what do they mimic? They mimic antennas. And what does that mean? It's going to conduct that radiation, and then it's going to actually flow inside my circuit and break it. This is extremely bad how this would be designed, if it's designed for a certain application. So there's one way of getting around this, or there's several ways, but one we're going to talk about is about putting a sheath over it. And there's different ways of doing it. We're literally going to protect it, and then that is going to act as a ground. And that means the electrons that might get absorbed is actually going to stay away from my circuit that's inside it, and it's going to be conducted away instead. It's going to protect it. And then we also need to make sure the connector does a tight seal, which we'll talk about in a minute. And there are different types of these sheaths around. I'm going to just talk about two of them. So one is this metal core conduit. It's a bit like a gooseneck. It's actually extremely robust. It can't actually be crushed, or it will take quite a lot. We've actually got it over on our stand if you want to go and have a look in a minute. But of course it's quite bulky. There's not a very good bend radius on it. So it's good for some applications and good for others. But of course that one could be water sealed as well if you needed. And then you have others as well, which are these types of braided cables, actually made up by many, many thin wires, which actually really helps if it's going to be installed in a certain way. And this is what we'll talk about. So I actually asked an application engineer, what is the best type of protection, best type of sheath that could be used? And it depends. It's not an easy answer. I was hoping for it to say, this is the best performance that you can get. But it's pointless me saying, well, the metal core conduit, that's the best you could use, because if you can't actually fit it inside of your device, then what's the point? It's not actually going to be useful. So it all depends. And the same happens with connectors as well. Which is the best connector out there to use? It depends. It depends on things like, okay, is it going to be power or signal inside it? So if it's going to be power, well, it's going to have to be a bigger, chunkier cable in order to let the current flow through it. Is it going to be what space is available? Maybe you've only got a tiny bit of area that you can dedicate to the connector itself. How tiny does it need to be? What weight is it? If you're doing something, for example, which is on a satellite, you need to really worry about the weight that's going up in there, so does it need to take care of that? Resistance to harsh environments. Where's it going to be used? Like the example I used earlier on. Does it need to survive in the Sahara Desert and survive also in Siberia? And also maybe it's on a ship and then it's going to have lots of salty air next to it. Does it need to be IP rated, similar to what I said a second ago? Does it need to be flexible? Is it going to be in a vibration type scenario? So maybe I've got those two boxes and one's moving around and the other one's moving around. Does it need to actually have some flex in it just because of where it's actually being used? The installation method. Any production engineers here? Okay. Well, I will say a key thing is production engineers is that design engineers, some of them, not everyone, obviously not yourselves, don't think about how actually how the product is being put together. So even though for the application it's trying to solve, it might be great, but actually to physically put it together, it can cause problems. And this is where also I get a part of my role is that I get the production engineers coming out and shouting at me, and it's like, oh, I wish that they'd spoken to me earlier because I know exactly the solution that should have been used instead. Would have solved their problem, but would have really helped out the production engineers later on. And even color. So if you have something, for example, on the outside of a tank, it might have to be olive green. So similar things. So it depends on the application. And the same goes for the sheath as well. And many, many more things to go with it. All right, so we've done the sheath. We looked at that. Let's go further along. And let's look a bit more at the application, like I said. And let's look at one in particular. So this is a swing arm. If you can imagine the installation method of it, maybe the person has to reach up quite high in order to get this in. Maybe there's a very small enclosed area, and there needs to be some strain relief on it. So therefore, this type of back shell, which goes on the back of the connector, is useful for that end application, taking into account everything that I just said. But that'll be different depending on what's it trying to be used. Okay, we've done the sheath, we've done the back shell, so now let's actually do the connector itself. How is that male and female part connecting together? Or also, maybe it's hermaphrodite. How is this actually going to connect? Are there any rules of thumb that can help us with that, with an EMC point of view? I'm going to simplify the diagram here, just for argument's sake. So I'm going to say the female part of the locking mechanisms on the outside, the male bits on the inside in yellow. Then there's going to be this keyed barrel on the inside. This is a certain type of connector. This is where if you've got two connectors of the same type, you want to make sure you don't put them in the wrong place. So actually there's little notches on the inside to make sure that doesn't happen. It's a popular option that can be used. I'm just going to cover the connector body in green. I'm going to spin this round so we can look into the connector as such, and this is what we're going to end up with. So you can imagine you've got the female and the male bit. They're actually screwing together with the threads they have there. But of course, that's a locking mechanism. It's designed for locking. It's not originally designed for EMC performance. So if I've got some electrons that have been received from some radiated interference, and then that's got to conduct along, well, that's not the first thought of it. So is there something that could be used to improve this? This is where in certain types of connectors, they actually have these springs that are put around the inside of it, which actually touch from that internal keyed part, this barrel that you have here. You can see the keying there. And actually, sorry, I'm in your way. And then actually that touches all the way around. So we have a 360-degree now area where we can have more confidence that there's going to be a greater current flow. And that, for example, on a Series 3D 38999, for example, is now part of the standards. So just something else to take into account. All right, we've done the sheath. Now we've done how the back shell, how it's getting on the connector. We've done the connector itself, but it's pointless doing that unless we're actually going to then worry about how is it grounding to the chassis itself. That's where you can use gaskets or elastomers that actually act as sponges. And these can actually compress together, and it gives another nice tight seal. And these can be made in multiple different sizes, multiple different methods, depending on your end application again. And it's just another way to make sure we have a nice tight seal all the way going through. And this can also be used if you have two metal boxes that just need to be connected together. Maybe it's not actually a connector, but you just need something that's adhesive that's going to make sure that it's connected together and you're not going to lose that EMC performance. And actually, a while back, I was speaking to a customer, and what he was thinking of doing, because he really wanted to use this certain style of connector, which wasn't a bulkhead connector. He wanted to connect it direct on the PCB. That would have meant a hole. So then we're actually looking at putting an elastomer like this around the inside of the PCB to protect it. It was another use of what it could be. It's very flexible. Sometimes, though, similar to the video cassette recorder, you can't avoid having holes in it. So for example, a fan, that could be another one. Maybe you need to make sure air is circulating in and out of it. You have to have this hole in order for it not to overheat, like we said earlier on. But that's where also you can have vents that are specifically designed for EMC purposes in order to close this as well, in whichever size is required according to it. So there's options out there. Even if there does have to be holes, there are options out there still to give that protection, which is available. Okay, we've done the sheath, we've done the back shell, we've done the connector, we've done the panel mount. Now we're going to go inside of the enclosure itself. And inside there actually is where some of the radiation can come from. It can actually come from a couple of these chips. And my first graduate job that I had actually was working for Sony, and I was an RF engineer working in their TV department. And so I was involved in when the TV would receive terrestrial signals, cable signals, satellite signals. But of course those are full-on RF problems or RF signals, and I'm literally bringing them inside of my enclosure where there's going to be all the devices that are actually controlling the television. We know that's not a good thing. So that's where at the start we always use these types of enclosures. Sony's very lucky because they would make about 5 million TVs, and not everyone has the luxury of having such a high quantity of products. So that meant they could make a customized size can, exactly the right size and shape for what they wanted, and they could make it cost effective because they were making 5 million of these. But if you're making a lower quantity, maybe up to 1 or 2 million or something like that, or way lower than that, it's not so affordable to make something custom made. So what's out there? What could we do up front? Well, for example, there's these shield cans here where you have these clips that are surface mounted in the same way that a resistor or capacitors would be as well. And then you easily can put them on top. And actually I've met some customers, and what they do is when they're designing their PCB, they will populate many areas of their board where they think, do you know what? Maybe that chip could give off a bit of radiation. I'm going to cover that as well. And they'll cover loads of their device. But then when they're doing the EMC testing, they'll gradually take them off and think, maybe actually out of the 6, I only needed 2. And it's a good way of using your knowledge. It's a good way of guessing and trying to get it in our favor to make sure we can get through those EMC tests later on. And then when they get to the production phase, they just don't bother mounting the clips. So they're just the copper pads are just left there. Yeah, sure, it sacrifices a bit of space, but it's a very good way of trying to think, right, I want to do some type of EMC protection up front. All right, so let's go back into the context of what I'm saying. Because is there a faster way? You're like, well, thanks for all this. This is really useful information, but I failed the EMC test. How is this actually going to solve it now? What can I do? First off, tiny bit of filter theory. This is, if I was to go in depth properly, this is like a proper university semester and more and more and more, right? So I'm going to try and go through this in about 1 minute. So let's see how I get on, right? This is an RC filter. This is a capacitor in the middle that we're going to talk about. It is 2 plates that are next to each other. What that does is it causes, when it has a signal that goes through it, it'll actually charge up and actually store the energy in it. So on my graph here, I've got time, I've got amplitude that are going there. Keep track of this graph because I will change it amongst frequency in a minute. And I'm going to put a step function in it, which is where I'm literally going to turn it off and then on and off and on, and I'm going to see what happens to the capacitor, what's actually coming out from it. And what I would have is that it will gradually charge up. When it is turned on, it would gradually work its way up until it had saturated. And then when the level had dropped, it would then drop down. Hopefully, you all should be familiar with this. And then if you increase the frequency, then actually you're removing the amount of time that it has to actually charge all the way up. And if we were to increase the frequency so much, you actually haven't got time for that capacitor to fully charge up before it needs to discharge. And that's why there's a drop in the amplitude there. Very brief, basic idea of filter theory here. So if now I'm looking at frequency that you can see here, we actually end up getting this type of performance for this type of capacitor, where you can see I have the different frequencies there. I can see the first one that I showed, right, it's well within the boundaries of being able to rise and drop. The next one was just on the cusp where it was going to go, and the last one, actually, it is now the amplitude has started to reduce. And this actually is a roll-off, and it comes off at a certain gradient, but just for argument's sake, it's 20 dBs per decade. Every time it goes up by 10, it's rolled off by 20 dBs. I'm trying to go through this very quickly, sorry. All right, but what happens if we had a different size capacitor? What does that actually do? So I've switched it back to time versus amplitude, and this time I'm just going to have a switch. I'm just going to turn it on, and I'm going to see the difference here. So that's the capacitor that we had before. Now I'm going to have a larger capacitor. So if it's bigger, it needs to have more time for it to fully charge up in it. So that's why it's actually slower. And then if I had an even bigger capacitor, it would take longer. And then if I was going to look at this at frequency versus amplitude, back to frequency, that's what it looked like before, you would end up getting these roll-offs at different areas here. So the bigger the capacitor, the further down it would go. So very briefly, idea. So using circuitry like this, say we have a noisy environment inside of a system, and we know that's actually what's causing either the conductive or radiative interference which is coming off it. Maybe we can use this somehow. But first of all, sorry, these are different types of filter that can be used. As I said, I'm brushing over it very quickly. The roll-off, like I said, that gradient actually depends on the setup. And actually you can have different types of filters, so a pi filter because of the shape, what it looks like. You can have a T filter. You choose that type depending on what you need, and also the internal the impedance, the source, and also the load impedance, which we haven't got time to go through today. But you can see we can actually have a good idea of trying to use this type of tool. And you can get a low pass filter, which is like what you see here, so it lets all the frequencies down here out and it will chop off the high ones. You can get a high pass filter where it'll only let through the ones up here and actually it will remove the ones further down. You can get a band pass filter where actually you'll have only the middle frequencies on a certain frequency that's chosen. And you can get a band stop filter, which is where it will let through everything else and it will only remove certain frequencies from it, which looks a bit like this. And then we can change the value of the capacitor, we can change how many capacitors are used in the circuitry inside it, and we can actually then choose what places that we actually want to remove from it. all right, this is very nice knowledge, Robert, but what's this going to do? I've got to go and tell my boss this problem, right? I've walked down the corridor. How good would it feel if you could, at the same time, when you walk down the corridor and you told your boss that it's failed? What about if you told him, don't worry, boss, I can fix it for you. I can solve this for you using this type of theory. And actually, you can have this device. And when I first heard about this, I couldn't believe it. Like I said, I'm a connector geek. And when I first discovered this, it's also I got a big background in EMC, I was like, this is brilliant for exactly the context that I'm trying to say it. Inside this type of seal here is a circuit. It is actually a electronic filter that can be inside it. And it can be put on different pins on it. So if you know this certain pin is giving me the problem, that's where the radiations come off of it, I can actually put a capacitor in the middle of it and I can ground it, or I can use it amongst different pins depending on what is needed. And we have the people who are in this company called Quell who are experts on this. They've been doing this for 20 years. So they're very much a case of once they have a failed test, that data can be sent to them and they can actually produce this very quickly for them. So here's the example of them. This is the failed test that they once had. They knew that it was coming out of the cable. They've just simply inserted this custom-made E-seal, it's called. It's get pushed in back with the connector, and look at the performance, how it's reduced. So how good would it be when you're going over to your boss and you're saying, or your customer, and saying, it's all right, we don't have to completely redesign the PCB, completely redesign everything. For those of you who've done a PCB that's actually very compact, you know if you move one thing, you have to end up moving everything else. And that's basically like doing a whole other project. But now with this, you've literally just shoved a filter on the end of your device. You don't have to do that anymore. As I said, they're custom made for whatever connector is needed. So that means if I've got this, and I've got this problem, instead of this terrible news that now is in everyone's mind, where you failed this test, actually, the redevelopment is a very short amount of time. It could only be 1 or 2 weeks, if not less. You'll have the testing, which would just be to continue what you had finished. You might be happy not needing to actually redo it, because redoing the temperature testing, for example, because these devices are designed for military applications. And that means, who knows? Maybe your actual testing isn't part of the critical path analysis. So that means actually your production might even be on schedule. Or at worst, you've got a new delivery date, which might be days or weeks, and not months or possibly even years by it being pulled out by using this device. That's why I love it so much, because I'm just thinking, my gosh, that would have been so useful in my past. Thank you very much, everyone. Our stand is right there. We actually have many different zones of, we have 8 different zones of products of different suppliers that get put next to us, full of different solutions. Yeah, please come along and say hi, and these are the suppliers that we have.